Hello, and welcome. Today, we're diving into a fascinating paradox that has puzzled physicists for over a century, Maxwell's demon. And we're going to see how it's getting a quantum makeover. Imagine a tiny, mischievous being, we call it Maxwell's demon. Back in 1867, physicist James Clerk Maxwell proposed this thought experiment. This demon, he imagined, could sort fast and slow-moving molecules in a gas, without expending any energy. Now, why is this a problem? Well, it seems to break one of the most fundamental laws of physics, the second law of thermodynamics. This law essentially says that disorder, or entropy, in a closed system always increases, or at best, stays the same. It never goes down on its own. Think of it like a room, it naturally gets messier over time, not cleaner. The second law dictates that you can't get work or energy from a closed system being at the same temperature, and that heat always goes from warm places to cold places, and that the transfer of heat will always create some waste. By separating the fast and slow molecules, the demon creates a temperature difference, and from that difference, you could theoretically extract work, like powering a tiny engine. It's as if the demon is creating energy out of nothing, seemingly defying the second law. This is the Maxwell's demon paradox. For a long time, physicists have tried to exorcise this demon. One popular solution involved the demon's memory. To sort the molecules, the demon needs to remember which are fast and which are slow. Erasing that memory, scientists argued, would require energy, and that energy cost would balance the books, saving the second law. But now, researchers at Nagoya University and the Slovak Academy of Sciences have taken a fresh look at Maxwell's demon, this time through the lens of quantum mechanics. And they've found something surprising. They created a mathematical model of a demonic engine, a system powered by this tiny sorter. They used a framework called quantum instruments to describe the most general forms of quantum measurement. Their model had 3 steps. The demon measures the system, extracts work by interacting with a thermal environment, and then erases its memory, also by interacting with that environment. They derived equations for the work expended by the demon and the work it extracted. These equations were based on quantum information measures. And the result? Well, under certain conditions allowed by quantum theory, the work extracted could actually exceed the work expended. It looked like, even after accounting for everything, the second law could be violated. It's like finding a hidden loophole in the rules of the universe. The researchers were as excited as they were surprised. It seemed quantum theory wasn't inherently demon-proof. But, and this is important, this doesn't mean the second law is actually broken. The researchers emphasize that while these quantum loopholes exist, you can always design a quantum process to comply with the second law. Think of it this way, quantum theory could potentially bend the rules, but it doesn't have to. Quantum mechanics and thermodynamics, while logically independent, can coexist in a remarkably harmonious way. Any quantum process can be realized without violating the second law. This might require adjusting things, or bringing some different systems into contact. This discovery has some pretty exciting implications. It helps us understand the thermodynamic limits of quantum systems. This is crucial for developing technologies like quantum computers and nanoscale engines. One of the key takeaways is that quantum theory doesn't know about the second law of thermodynamics. It's logically independent. Yet, any quantum process can be made to comply with it. It's a delicate balance, a fascinating interplay between these fundamental principles. So, Maxwell's demon may have found a few quantum loopholes, but it hasn't overthrown the second law. Instead, it's showing us the intricate dance between quantum mechanics and thermodynamics, a dance that could pave the way for incredible technological advancements in the future. It's a reminder that even the most established laws of physics are still full of surprises.